Alright, today we're going to be doing homework 4, part D. What's important about this is that we're going to be using this table down here when doing our PID model and using PI to solve part C through E. What I want to get through first is I want to talk about what we've been talking about and what we've been doing. So homework 4D, it has 2 tanks in series, and it's going to have QC, which is the control flow in, because we're going to control the flow in to get a desired height at our second tank, which will then obviously impact the outlet flow. Q1 right here is going to be Q2, but just ignore that for right now. So we're going to go from QC to GP1, which is just tank 1, and that's going to have a general process. And then we're going to go to tank 2, and that's going to be Q2, Q1, Q2, same thing. And that's going to go to tank 2 right here. And that's going to give us a certain height that we want to get to. And then here's the process of what it looks like, and then the overall transfer function process is right here. And so when we did that in code, we actually did it from QC to Q2, and then we did Q2 to H2, because those are 2 different transfer functions, and then we multiply those 2 transfer functions together. And what we're going to do today is we're actually going to use that general process to generate 50-point synthetic data for the step response to the previous tanks in series. Alright, let's get started. So as we see right here, QC to H2 is the multiplication of those 2, and then our transfer process forward is including the PID. So we're not going to include the PID in ours, just the transfer process, and that's how we're going to get started with our code today. So T underscore exp is going to be equal to np.linspace 0 to 15 to 50, and then we're going to be looking for the H, so we're not worried about that first. And this is going to be a height 2 of the experimental, and then that's going to equal to our step function of the transfer process, so QC to H2 dot step of shift T equals to T square exp. And then when we do our chart, we're going to hopefully, we want our data points to be in line with the H2 experimental. So just to make sure that's in progress, we're going to put range dot normal. We're going to do our location equal to H2 underscore exp, and then we're going to have a standard deviation as per the problem of 0.02. So SEALE is going to be equal to 0.02, and then we're going to hit enter. And we're going to put in our random number generator, so RNG dot numpy.random state, shift enter. Alright, and then we want to graph that. So fig equals make underscore subplots, and then we're going to do fig dot add underscore scatter. It's going to be x is going to be equal to t underscore exp, while y is going to be equal to h2, our set points, different experimental set points. And we're going to look at that as dots on a chart so that it can make it look easier for us later on. And then fig update underscore layout is going to be w.eth equal to 600 and he.ght equal to 400. Template is going to be poly underscore dart. You know how we do it. Add underscore scattered. Mode equals markers. Oh, makers. Huh. I'm thinking about getting drunk later apparently. All right. And so what you see here is that this S curve, what you see, what we want to focus on right now is this little box right here. Yep, right here. This is what we want to be worried about, because this is how we're going to do so fit the data from D1A using FOPTD model by minimizing the sum square error between the model and the data. So to minimize the sum square error is to get rid of this portion, I would say, right here, because if we look at it, we see that the graph starts right here, but there's a portion of the curve that's just not being used, because obviously to go from tank 1 to tank 2 takes some time. So we want to get rid of that when doing our calculation. So we're going to go from 0 to just about 1, I'd say maybe about 0.8, and we're going to take that down and we're going to call that theta. So when we call that theta, what that does is we're able to put it into our overall equation for finding the y for our S curve, and we're going to subtract our x component by the theta, because theta is an x component, so time minus theta is going to help us when evaluating our y values for this S curve. And the S curve equation is going to be given by this equation right here. It's going to be the proportional controller of 1 minus the exponent of time over tau. Tau is just a constant variable. While to get rid of the S curve with the theta, we're going to be subtracting the theta from the t. So how can we get started with this? We need to fit the data from D1A using FOPTD model by minimizing the sum square error between the model and the data. Alright. So let's define our FOPTD model. That's going to be V in there. So K, comma, tau, comma, theta are different variables. Going to equal to V. And then Y is going to be equal to this equation right here. Control C, Control V. K is time. That's JMP dot exponent. And then T minus theta divided by tau. And T is not just any T, but T underscore EXP. And this is going to return to us a JMP dot where, I believe, JMP dot where of T underscore EXP is greater than or less than theta, and then comma 0 dot comma y. What's wrong with it? The parentheses. Alright, so where are we going wrong here? T underscore EXP greater than theta and comma 0 dot y. Shift enter. Oh, what is this? Delete. Shift enter. Okay, thank you. And then we want to have a guess for that. So V underscore GUESS is going to be 2 dot. Define our SSE as V, and we just want to return repeat sum of H2 underscore EXP as FOP TD of V. tuple, object is not callable. Define SSE is V. Return JMP dot sum of H2. Yes, because what we're trying to do is determine the optimal ID controller to time for controller. Okay. Okay. And then now we want to plot that. So fig dot add underscore scatter x equals t underscore exp comma y equals FOPTD of res dot x. Oh, we need to do the minimize function of res dot x comma mode equals lines, and then so we use from SciPy import minimize. In order to use that, we're going to do res is equal to numpy dot minimize, not numpy, minimize so first argument x is going to be t underscore exp, and then, well, just going to get SSE, comma FOPTD, what's wrong, self.x, wait. Minimize, alright. And then we went here, and then import root minimize, import root, initial value. We need a guess. We need an initial guess. This is, that's why. V underscore G U E S S. Alright, and now you can see the difference between the two. What we want to do now is we want to, from D1B, determine the optimal ITAE controller gain and reset time for PI controller. So, alright, and that's what this was right here. And now what we can do is we can simulate the closure response to the two Tengen series model that are received for PI controller. So PI controller, going to come down here, PI, P, A is 0.586, and B is negative 0.916, and for the I, 1.03B, and then negative 0.165B, and then Y is in correlation to A, so this A right here, and then theta, we know what theta, we know tau from the variables, and then B is up here, and then, so KC is actually going to be equal to Y divided by K. So let's first define what KC is going to be equal to. The proportional mode, T9, derivative mode. Alright, so we're going to go here, and then we're going to do K. Do we use K or regular K? K. K, comma, TAU, comma, TAGTA. And then what we're going to do is we're going to make that equal to res.x. And then KC is going to be equal to Y divided by K, and Y is equal to A, so 0.506, 0.586. And it's going to be times TAU divided by TAGTA right over tau. And then that entirety is going to be times the negative 0.916, and all that divided by K there. We'll shift it. Alright. And then we need to do tau. TAU is equal to okay, and then that's times TAGTA over TAU, and then this is tau D, tau I, tau is equal to this over, no, tau is equal to Ti times A, so Ti is equal to tau over that. Is still equal to 0, shift enter. And then we want to do the same thing, but without using our ones from before. So shift enter. Alright. Now we can look at our new codes and see what we have. Okay, and now we want to go to we want to perform a Bode frequency response analysis, and we also want to look at this around here. Bode response. So W equals 1P dot 1 space negative 2 comma point 0.02. So this bin right here at negative 20, we're going to go right, well, at 0, when it crosses it, we're at 04. Right here at this little bend right here, negative 20.464. 464. So from here to 180, it's going to be our phase shift. And -2, -2.